All righty. Yeah. Try this through the computer, that way we know what's going on. Okay, so hanging on the lecture desk is a mass with a couple of springs, and we are going to be studying a phenomenon called Hooke's law, which is the behavior of springs or any elastic object and we're really talking about the relationship between the stretch, and when I say stretch, it can also mean compression, and the applied force. Okay. If we were to graph this relationship, force in newtons versus stretch in meters. Computer not working or just almost dying? Okay, great. And we've talked a little bit about this because we did, I believe, graph this when we studied elastic potential energy. So if you thought of this just like a going into the grocery store and taking bananas that had perfectly even mass, and putting a banana on a veggie scale in the grocery store, and then watching the dial move, every banana that you added would move the dial an equal distance. So let's say that one banana moves the dial 10 centimeters. 2 bananas would move the dial how far? 20. 3 bananas, 30, and so on. What's the relationship then between force and stretch? Mm-hmm. Direct or linear, that's correct. The slope of this line, is my mic cutting out? It's red, so it's not happy. This other one, I think this other one isn't working. Is this one? No, this one's not working at all, is it? Nope. Okay. If it gets annoying, let me know. Oh, all right. Why don't we just turn it off? I'll just turn it off. Wow, that was quick. Way to communicate your feelings. So the slope of this line is the spring constant. And we use the letter K, and the units are newtons per meter. Y over X, newtons per meter. If we look at our springs, and so now I need a friend. And would you come up here and try to flip that so that Hannah can see this?
Well,
That's all right. I'm sideways. Actually, it's kind of working. Yeah, I think you can.
how would I get that?
So that's fine.
Oh, that didn't work.
It's actually fine here. I think it doesn't matter.
You shouldn't just turn my head.
No, I think it's actually, because on my computer no, it's sideways. I'm just loony. There we go. Rotate. Okay, I don't think it rotates. I have done it. You're right. on the dock cam.
Rotate. Do I just
Sure.
press it? Oh,
There we go.
that's
Upside down. That's all right. And one more time. There we go. We did it. Yay. I knew we had a way. All right.
Good.
This is for you, Sahana. Okay.
Get you
So
in there.
you can see we have two springs. Are you watching me or are you watching
He is.
this me? Duck cam me. You're watching me, Ian. All right. So of these two springs, the one on the right versus the one on the left, the one on the right, and the one on the left. Wow. Can you tell by looking which one has the larger spring constant? The one, okay, I just gave you left and right on purpose. The one on the right or the one on the left? Which one has the bigger spring constant?
The larger, no, that one. The one bouncing right now.
This has the bigger spring constant?
Yeah.
Patrick said it, so.
Wait. No, it's all the way around, all the way around, all the way around.
Woo!
Yeah.
He was like this.
Well, I had to like,
It's right there.
I get my slow back.
Yeah, this is correct. The more tightly sprung spring has the bigger spring constant. So it takes more force to stretch it, okay? We eventually, by the way, and I'll use this one because it's a little bit more obvious. Eventually, we're going to take this idea and then move it. And so that's actually really complicated, believe it or not. That motion is very complicated. It is a non-constant acceleration. It is in something called simple harmonic motion. It has the properties of anything that has a regular, repetitive, oscillatory type nature. If you make it like three-dimensional, so if I like pull it on an angle, it does all kinds of crazy things, and it never has the same pattern twice.
Yeah.
Whee! Yes, sir.
Does that mean we're gonna learn chaos theory?
No. All right. But you get the idea here, right?
Yeah.
Okay. All right. So to finish this, oh, hello, that's right. Got it all rotated now. That's more sideways. La 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 la. There we go. Okay. So the equation that we have here is the force applied to a spring is equal to the spring constant times the distance that we stretch it. Now that should look very, very familiar. When we were doing sheet problems, we said elastic potential energy is 1/2 kx squared. And from, this is Hooke's law right here, F equals kx. K times x, if we don't worry about the square, what would that be? Force, correct? And then we have to carry down the x. And force times distance is work, right? What's the 1/2 for? Any idea? No? We just finished all that rotation stuff. Good guess.
Once it starts pushing, once it's halfway, the rate of pushing is gonna slow down, so like, once it's halfway expanded, it doesn't push anymore, now the spring's gonna be like slowing down.
Pulling, yeah.
The block is gonna go, yeah.
Yeah, that's not why, you're right, but that's not why this 1/2. Dang, it's not a good day for Patrick. He's usually right on the money. It's the average. It's the energy that's captured here. And what shape is that? Triangle. So it's the average work done. At the beginning, when you start pulling this spring, takes very little to no force, right? And then as we pull harder and harder and harder, it goes farther and farther. Okay. By the way, what you were talking about, Patrick, is true, and that's when it gets complicated. We'll talk about that tomorrow. There's one other phenomenon that I think probably a lot of you are familiar with, and that is if you pull it too hard, Oh, bad things happen. Kill the slinky, exactly right. You have exceeded the elastic limit. And this will usually cause permanent deformation. Here's an example. Oh, sad. How do we know that that has been pulled beyond its elastic limit? Yeah. It doesn't look pretty, yeah. The spacing between the coils is not even, and Dennis said it correctly, it's not really returned to that original nice, tightly packed coiled shape that it had when it was a brand new spring. So yes, naughty physics students that got carried away in the lab. Tonight's homework, and I'm just doing this for Sahana so we can get it on the video, is 12A number 3 and number 5. And here's Sahana. We're talking about and to you, because no, you're fine. We're recording for you right now. Yeah. All right.